So firstly, welcome to the Adam Dissemination event. We're joined by some excellent speakers this morning, and we'll also have a Q&A panel later on and give you the opportunity. But first, a few housekeeping rules, if I may. So housekeeping wise, most of you are probably fairly familiar with how a webinar or Zoom webinar works. There's a Q&A box at the bottom. Please do use this Q&A box at any point during the next hour and a half to put any questions you'd like to anybody, myself, our guest presenters that I'll introduce you to shortly, or for the panel later on. Do ask any questions. We will select some of those questions, and we will also give you the opportunity, should you wish, to ask those questions live of us. There's also a chat function. Feel free to chat amongst yourselves, or if you have any technical issues, then raise those, and Mary is online and she will try and help and guide you wherever appropriate. We are going to record today's event. It's really useful. As part of the funded project, we need to share the successes, learnings and new capabilities off the back of the projects. And this serves as evidence that we are sharing it, but it also allows us to record and take appropriate minutes. And lastly, right at the end of the webinar, you'll be asked to fill in a very short survey just to allow us to improve future events and give feedback to the presenters. So just to reintroduce myself, my name is Bradley Wicks. For those who don't know me, I am the CEO of the Institute of Digital Engineering, and I also am the co-chair of the Advancing Digitalization Mission for the Automotive Council. Our remit is broad and yet relatively simple. It's to look at upgrading or re-engineering the way we engineer product in the UK by embracing new science and technology. We know that the automotive sector is rapidly entering brand new territory as the world tries to create future mobility solutions, and each nation will vie for defining those architectures. We need to ensure the UK is at the front of those developments, as those countries that develop those new architectures have a far amplified say in where the value chains that deliver those architectures sit, and also the manufacturing footprint. So in the UK has to lead the development of those future mobility solutions. And that is more than just batteries. So I think in terms of the agenda today, I'm not going to say very much more than that. I'll talk a bit more later. We are joined by Pierre Carugno from McLaren Automotive. Pierre is the senior aerothermal engineer for McLaren. And we are joined by Professor Gary Page, who's chair of computational aerodynamics at Loughborough University. Two great speakers. They're the two leaders on this project, and they will give you some insight in terms of more detail on the project, but also some of the progress that has been made. We'll then importantly get to the interactive session where Pierre and Gary will join me, and I'll try and moderate a panel. We'll be joined by Dr. Yves Zhang and Arthur Slight from McLaren as well. And that's your opportunity to learn more and get behind some of the slides that you'll see today. And then right at the end, we'll try and draw some conclusions, take you through some next steps, and tell a bit more about the digitalization roadmap that we're doing in parallel with this exercise. So I think with no further ado, I think it's probably worth getting straight into the main presentation. So if I can introduce you to Pierre. Pierre, are you okay to put your slides?
Yes.
Lovely. Thanks very much indeed.
Please do let me know if you can see my slides.
We can, thank you.
Okay, perfect. All right, so good morning all. My name is Pierre Carugno and I'm a senior aerothermal engineer at McLaren Automotive. Today, my presentation will be about McLaren Automotive's challenges and opportunities in a world driven by data. Before starting, I'd like to thank the Institute of Digital Engineering for funding Project Adam and for the opportunity to speak at this webinar. So I want to start my presentation with this picture, and this picture represents really how McLaren Automotive is a creator of luxury, high-performance sports cars and supercars. Every vehicle is hand-assembled at the McLaren Production Center in Woking, Surrey, and designed here at the McLaren Technology Center that you can see in the background. McLaren Automotive is a pioneer that continuously pushes the boundaries, and this picture here is really showing how each vehicle that we design is pushing further the boundaries of what's possible from an aerothermal point of view. And it's key to highlight how each vehicle is really instrumental in enabling the pursuit of our aerothermal mission and vision. In a world driven by data, our aim is still to provide the best aerothermal solutions for all our cars by embracing the challenges and opportunities presented to us. And there's never been a better time to actually spell out our vision, our purpose really, as to virtually design, implement, and validate the best aerothermal solution for all future McLaren platforms, and to achieve our mission of providing the best aerothermal solution for all our cars. As aerothermal engineers, we are constantly generating CFD, wind tunnel, and track data for our vehicles. And here we've got 3 pictures of the McLaren Elva at 3 different development stages of the project. And with the continuous creation of data comes great responsibilities. And our mission to provide the best aerothermal solution for all our supercars must be supported by 3 key pillars. The first one is accelerated validation of key aero attributes. The second one is accelerated aerothermal design throughout product life cycle. And the third one is increased confidence in the aerothermal development of new vehicles. So how have Project Adam and the Institute of Digital Engineering helped the development of these 3 key pillars? Project Adam enabled Loughborough University to use digital engineering tools on hundreds of McLaren Aerothermal's legacy wind tunnel test and CFD data points, helping McLaren uncover trends, blind spot, and correlations that are now readily available to be used by our thermal engineers during future vehicle developments. This is simplistically shown here in this picture at the bottom, where we've got, rather than a black box, I used a McLaren orange box, which is Gary is going to talk about later, effectively providing a connection and an enabler for our data to unlock deltas, trends, and confidence bands by adopting digital engineering techniques. Finally, looking at the bigger picture, Project Adam helped McLaren and has helped McLaren unlocking 4 key aspects. The first 2 are a higher technology readiness level for our prediction tools and increased confidence in our virtual design tools, effectively accelerating the validation of key aero attributes. The third aspect is about showing how a full virtual validation and virtual aerothermal design development don't feel anymore too far away in the future, and we can actually drive and design our technology roadmaps to accelerate a full virtual vehicle validation even more, thanks to Project Adam. Finally, the fourth and final one is about equipping really our aerothermal engineers with increased data-driven decision-making capability at project level to help taking the best and most robust choices from a risk management point of view. This concludes my very short presentation, and along with Arthur, our head of aerothermal, we will be happy to take any questions in the Q&A session afterwards. Thank you.
Thank you very much, Piera. A fantastic summary of the project, and I know we'll have some interesting discussion later in more depth. So let me now introduce you to Professor Gary Page. Gary, are you there? I'm hoping, there he is. There he is. Fantastic. Gary, are you okay to take us through your presentation?
Yeah, so you can hear me. Can you hear me correctly?
We can, yeah, perfect.
Excellent, yeah.
Gary. Over to you.
Okay, thanks for the introduction, Piera. Yeah, so my name's Gary Page, and you can see from my title underneath that really I'm an aerodynamics and a CFD person. And you can see that the other half of this work is really the machine learning aspect. And so for that, we need to thank Yves Zhang, who's the other academic involved in this project, who's had huge input in terms of that element. And like all university projects, in reality, the hard work is done by the researchers. So Joe Page and Victor Martino Parry have worked really hard in quite difficult circumstances of lockdown to deliver this project sort of on time. So Joe worked on the Gaussian process regression and Victor on the CFD side. So that's the introduction. And really, so what's our starting point here? So Piera's given us a little bit of background, and the way we interpret that is how can we exploit previous data, so historic CFD simulations, wind tunnel tests. Surely we can use previous data to do a better and a faster aerodynamic design instead of doing everything completely from scratch. And more specific is how can we use CFD to predict the wind tunnel measurements? And this is a classic sort of delta type approach that aerodynamics often use. And indeed, you know, we could also use this technique for how do we predict the delta from CFD to track testing, or vice versa. We can use track testing to predict CFD if you really wanted to do that. But as you'll see, it's more than a simple delta. What we're really going to come up with is a technique that allows you to go between one and the other, that the delta is itself a function of the geometry of the vehicle and the type of vehicle. So the other thing we want to do is figure out how important certain things are. So engineers have their own ideas if they want to meet a target attribute, say for drag or lift, what things they should change and how to achieve that. And we want to use the data to actually come up with really what are the most important parameters to use to achieve what you want. So what we're aiming to achieve, and we've pretty much almost achieved that, is a single aerodynamic model that takes all past CFD wind tunnel. And the bit we haven't yet done is the road testing for multiple cars and variants. So the single model can predict any car with any parameter. So just taking a little bit of a step back, one of the things you'll see with machine learning approaches is in general they need a lot of data. The technique we're using, Gaussian process regression, is not so bad for that, but nevertheless you need a lot of solutions. So one of the sort of parallel aspects of this is automatically extracting parameters from past calculations, because it may be that the past calculations have not been well defined in terms of things like wing angle or ride height or whatever. And so we need to sort of confirm that actually what the CFD simulation was, what you think it is, etc. We may want to extract new things from that simulations. So the piece of work that Victor did was fairly specific to McLaren. So this is, you know, working with McLaren's ways of setting up CFD and using star CCM, which is a bit of a contrast to the regression aspect, which is actually completely generic and doesn't really even need to be aerodynamic data. And in essence, what it is that star has its own ability to have Java macros inside that you can run to do various things. And so what we have is down the bottom right-hand corner here, a general sort of flow chart in terms of a piece of Python code which will generate commands to launch star CCM and then to run the macros. And the macros will extract geometric parameters sometimes directly and write them to a file, or sometimes we'll extract geometry out. We then use the bit of Python to then further process that and extract various parameters and write that out. And essentially these parameters, as you'll see, is just a table of numbers. So all the geometrical parameters we're interested in. So this is one example, and so Victor's done quite a lot of different attributes, but this is just one example. The first thing to point out is, although we have demonstrated this on actual McLaren simulations, what I'm showing here is a publicly available CAD. So that McLaren P1, you can go on to GrabCAD and download what looks like quite a complete piece of CAD. And what we're interested in this example is this rear wing. So the rear wing is relatively complicated in that it may have a variable height, it may have a variable angle, and its profile is not that simple either. So the simplest example here is where we use the macros within star to slice through the wing and extract the data points of the wing. And then it's a really simple matter to find the leading and the trailing edge and then figure out the angle. And because the leading and trailing edges are quite sharp, that's relatively straightforward. The other thing we want is the wing area. And if we just looked at the projected area in the Z direction, then as the wing changes angle, the projected area would change, which is something, you know, that's not correct because the wing area itself hasn't. And so then what we do is change our viewpoint by rotating through that alpha. So we're now normal to this purple line here, and then take the projected area in that direction. So that way the area of the wing is independent of the angle that it's at. Then there's a few other things you have to be a bit careful of. So one is correction for right height or rake. So the CFD is generally set up in a wind tunnel coordinate system rather than the vehicle coordinate system. So the angles we extract from that wing are based upon the wind tunnel. And one of the problems is that if you make the car at a really different ride height, as we're showing here, which is sort of exaggerated, then as we change the ride height at the rear of the car, it changes the angle we're measuring from the wing. And that's quite critical for machine learning, because what will happen if we then put that wing angle into the machine learning model, we'll get a change in lift and drag, and it won't know whether to attribute that to the change in ride height or the change in wing angle, where in reality the wing is not changing relative to the car, it's only the ride height. So again, that's relatively simple in terms of measuring the ride height and subtracting that out. So it's not a complicated thing to do, but it's quite important to ensure that your input parameters are independent of each other, because if they're dependent upon each other, the machine learning can't figure out which one is the important one. So Victor's done that for around 15 parameters. So for example, at wing, we also look at halfway out the angle and look at twist. And it's relatively easily extensible to more. So for example, you have a device that looks a bit like a wing, you can take the technique to do that. And it also currently will work on like folders of solutions and traverse them, pulling out the data and creating it fairly automatically. And typically it's a few minutes for each solution. So probably within a few hours, depending how many you've got, you can pull all your data out from a set of tests. Okay, so that's a little bit of an aside in terms of some of the things you need to do, which comes that message, you need plenty of data. And I'm going to go sort of actually into the actual regression aspect. So what we're using is a technique called Gaussian process regression. And fundamentally, like any type of regression, what we've got a set of data. And the key thing about this technique is the data can be quite noisy. It's designed to deal with noisy data. And I've also put the word observations in there because one of the things we found this project is translating between the computer science language and the engineering language. To computer scientists, it's an observation rather than a data point. And essentially, you know, to sum up, we want to fit a function to that data and we want to use it to make predictions of other data points. And in a few sentences, that sums up, you know, what is actually quite a complicated process. So if I give you a bunch of data points, and there's an example at the bottom here that's an online tutorial, which is a good explanation of this. So in this example, I've got a bunch of data points of the crosses. So that's our observations or our data. And I give that to you with a nice colored pen. You can draw lots of curves through that. And that's what the computer can do as well. So what you then have is which of those are most likely. So you can see the green curves where we don't have much data are quite extreme. It's probably unlikely the data will be doing that, but we don't know. So you can start to see by doing this, we're starting to generate a probability distribution of what's going on. You can also see here where we have data that's clustered quite closely together. There's clearly limited aspect for different functions to fit through that. So what the Gaussian process regression does is essentially determine what that distribution is to get the most likely function and essentially a probability of that. So what it comes up with is a mean prediction combined with uncertainty. So the example on the right, again, is available online from the Sheffield Machine Learning Group, and it's the software we've been using called GPy. And what this is essentially they've taken the sin x, a y equals sin x function, and they've computed x at sort of various points, so it's not uniformly distributed. Then they've added a bit of noise to the y, give it to that piece of software and say what should the function look like. So the software correctly predicts, reproduces the sine function, but you can see over here where we don't have much data, it's now saying I'm not so confident. So this is a 95% confidence interval. So where there's little data, it's less confident. You can see it here perhaps where randomly there wasn't much data, it gets a little bit wider. The other thing to point out is this particular data set, just through the randomness, had a few clustered quite close together with quite a bit of noise. And so one of the parameters in these type of models is a length scale to determine how things should behave. And it's part of, you know, the sort of tuning of this. And because the length scale is set correctly, it tries not to fit through that. It sees that as noise rather than as part of the signal. So it correctly fits through that. So that's essentially what we're trying to achieve, but this is all 1D. And if you go online, lots of the books and examples are all 1D, but we need data that's much more complicated than that. So in practice, what we have is, instead of X as input as Y output, we have multiple X, X1, X2, X3, and so on, and multiple outputs. So lift, drag, moment, etc. So that's just like, imagine a big Excel table with a column headings and lots of numbers. The other thing we do is have flags in the data. So there may be columns which indicate whether this data source is CFD or wind tunnel, and also be columns saying what car type it is, because we need to be able to let the model understand the structure of the data. So clearly, if it's one car type, it fits all the data through that, rather than combining them, trying to fit. It can't fit a single curve through all the cars. So it's fitting a curve through a car, but it's basing it upon other cars as well. And we can do different things you'll see in a little while. So where we started was called a bespoke model, where we take a single car CFD and wind tunnel and fit a model to that. And that model can then tell you what the CFD and the wind tunnel would be for that car. And I'll show an example of that in a little while. Then a co-regionalized model, which is all the data combined. So this is where we have the complete set of data in one model, and depending on what you ask it, it can predict any car and any CFD or any wind tunnel. And the reason, so we found the co-regionalized is obviously more complicated, but doesn't really suffer particularly in accuracy. It's almost as accurate as a bespoke model. And the reason you'd have a bespoke model is if you have some type of geometry as in a single car that's not present in others, that makes it more complicated to the co-regionalized. The other point is when you look at this, there are quite a lot of implementations and toolkits available, generally developed by computer scientists without a huge amount of application to engineering. They tend to be very simple examples. But the good thing is they tend to be open source. So the challenge is really, when you've picked one of these packages, is then to understand how the underlying parameters work in terms of choice of kernel, hyperparameters, length scale, and so on. And that's basically something I'm just not going to cover in here. So I could have done this presentation with pages and pages of maths, because that's what there is behind this, and lots of testing of different kernels. And that's what Joe did, quite a lot of work of what's the best kernels and what's the best parameters. So there's quite a lot of work in the background, which I'm not showing. So in some respects, I want to make this look too easy. It's not. This is quite tricky, but nevertheless, if you do it correctly, you get good answers. So what did we have? Well, we had around 800 data points, and they were spread quite unevenly over a number of cars. So it wasn't, there was, some cars had a lot of data, some cars had much less data. We also had CFD and wind tunnel data, but some cars only had one of those sources. So some might, would have been complete. So it's real data. It's not the sort of artificial data that often the computer scientists use to test their methods. And each data point has 7 values, 7 standard inputs, and 3 measured outputs. So in terms of presentation, I'm not going to say what they are. They're sort of, McLaren don't want me to, for good reasons, to explain what those things are. And in fact, you can do all of this type of work without knowing what they are, because as I'll emphasize later, it's just data. And we also have these modification inputs in some data points. So in some cases, certain aerodynamic devices, such as a side skirt or some other little aerodynamic tweak, may be off and on, and that's present in the data as well. Right, so what can we do? Okay, so I need to take this quite slowly because this looks like a simple graph. There's a lot going on here. So we have a 7-dimensional number of inputs. So to plot the data, I need 7 dimensions, which is clearly not going to happen. So what we have to do is to show, say, a variation of one input, how drag varies in this example against input 6. And we're slicing through this design space. So we have to fix all the other parameters. The other 6 parameters have got to be fixed. And the way we've done that typically is to look at the data we have and find the most common occurrence of, say, the value for input 1, and we call that our baseline. That may not be the baseline the engineers used when they did the CFD or the wind tunnel testing, but nevertheless, it's the most common occurring one, so that the slices we do are more likely to be where the data is. So what we have here is two different sources of data. One of them happens to be CFD, one of them happens to be wind tunnel. And you can see in terms of those red and the blue lines, some have more data and some have less. So the first thing is looking at the blue line. You can see we've got a mean prediction and we've got a confidence, and we've got some data points we've plotted. But note we've used the word closest. So the word closest is because some of these points may actually be exactly on the slice. Some may be slightly out of the plane. So maybe this point over here, input 1 is not quite the baseline. It's slightly removed. And if we make it precisely on the slice, we often lose points. So that's why these 2 points are not within the 95% confidence, because they're actually slightly out of the page, as it were, in terms of if we could plot this in multiple dimensions. But the really neat thing is that although for source 2 we only had to do 2 data points, it's used source 1 data to figure out the shape and has come up with a curve rather than a straight line. And also it's showing its confidence here. So although it's predicting what it should do at these higher values of input 6, its confidence is now is decreasing because it just doesn't have the data. It doesn't have the real data, and it's now started to rely more and more upon source 1's data. But if you think about that's quite powerful. So if in terms of an engineer is asked, well, you've done these 2 tests, if we make input 6 this value here, whatever this value, this white line might be, the engineer would say, well, actually I would predict the drag for that particular input 6 value of whatever to be a certain number, but also I can tell you with a 95% confidence it will be no worse than this number. So it gives you confidence in terms of your predictions, even without having to do a CFD calculation or do a wind tunnel test. And in terms of accuracy, where standard sort of machine learning type approach is you create a model for something, be it image recognition or whatever, and then you run the data you've trained the model on back through the model to check whether it actually works. And so essentially what we're doing here is taking every single data point for car A, putting it back into the model and plotting what the drag that it actually predicts compared to the drag should be. And if the predict and the actual are the same, we'll get a slope of unity 1 here. We'll get a straight line. All the points will be on a gradient to 1. And that's pretty much what we see. What we do see is a small RMS error, and that's essentially the noise in the data. If the data is slightly noisy, you saw with the sin X fit through that, it can't necessarily fit every point because it's slightly noisy. And this is one of the lift components, and you get the same trend. We get a pretty good accuracy, but it's now gone up a little bit in terms of the RMS error, and that seems to be a bit more noise in the lift data. So this is how well does the model predict data it has seen, and at the very end I'll show you how well does the model predict data it hasn't seen. So what's the problem with the bespoke model? Well, a good example is car E. So car E only has one source of data. It doesn't have the second source. In this case, it's got source 2. So we can plot source 2, but I can't predict source 1 because I've got no data. I've got no reference points whatsoever. So it can't use anything from source 2 to predict source 1 because it just has nothing. And that's where the co-regionalized model really works. So the co-regionalized model, this is the same car. And in fact, this is the same data. So this is the thing I was plotting on the previous page, but because we changed the scale, it's now near the bottom looking slightly less curved. But essentially the co-regionalized model has got multiple cars, starting with car A, and it's got multiple data for source 1 and source 2. And using all that data, it's figured out for car E that the drag, if for source 1, should be up here. So it's essentially done a CFD wind tunnel type correction saying this is what the answer should be. and it's got a reasonably confident prediction as well. These are reasonably tight. So considering this is, it's predicting something that doesn't yet exist, but based upon historic data, this is what it's saying it should do. Nevertheless, if you look at it, it is pretty much a straight delta. It is just shifting it up to a certain extent, and that's what it sees in the data. In comparison, if you look at one of the lift components, it's fairly confident how to fit the data to its own source 2, but it's less confident about what it should be for source 1. So it's giving a prediction for source 1, but the confidence bound is much, much more. And that's probably because it sees less correlation and there's more noise in the data for lift 1. But nevertheless, you know, it does a pretty good job of producing. And in this case, what you're getting, if you want to think of it as a classic sort of delta, the delta at low values of input 1 is smaller than the delta for high values of input 1. So it's producing a correction that is a function of all the geometric inputs. And in this case, we're just showing input 1. So that's the real sort of power of the co-regionalized model, that with essentially no data or limited amounts of data, you can predict things. So if, for example, we did take some measurements for source 1 and start filling them in, it would then regenerate the model and make this more and more confident. The other great thing about some of the machine learning techniques is they have ways of processing the model to understand importance. So there's a technique called Sobol indices, which is a bit of post-processing, which actually takes a few hours to run, but you typically only do this once. And what I remember, the point is that all the stuff we've done essentially has been run on a 5-year-old laptop, and it takes minutes. This is not computationally expensive. This is the most expensive thing we did, and it's a few hours. But it basically does a Monte Carlo testing on the model and then figures out how does the various inputs affect outputs. So how can we explain the output variance for the drag and the 2 lifts? So what this is saying is input 1 is very dominant for lift 1, input 2 is less dominant, and they both affect drag around the same, and input 1 and input 2 really don't affect lift 2. And input 3 is quite interesting in that it's saying it has very little impact. It cannot explain the output based really on input 3. And actually, perhaps our conclusion should be that input 3 is not influencing the outputs, and so we should probably remove it from the data. And then input 6 is quite a different parameter, and it clearly affects lift 2, and it affects drag, but it doesn't affect lift 1. So this hopefully will actually confirm what the engineers felt was the correct behavior. But nevertheless, this is what the data is telling us, irrespective of what people think may be affecting the data. So I talked about deltas in terms of going between, say wind tunnel and CFD. We can also look at deltas for specific modifications. So these are a pair of modifications that were apparent in the data where a bit of geometry was switched off and on. And although we've taken the scales off, you can clearly figure out this is 0, and how switching modification 1 on reduces drag, increases lift, and modification 2 effectively reduces both drag and 1 lift and has a big impact on another lift. So it gives you a simple rule of thumb. So this can tell, we could produce a table of, if these modifications, we'd broadly expect this type of change to occur. But we can do a lot better than that, in that we can do it as a function. So it's essentially the same type of information where modification 6 is switched off and on, and we look at what's the change in the output for drag and the 2 lift. But we're now plotting it as against a geometric parameter. So what it's saying is, particularly say lift 2, at low values of input 2, we're getting a certain delta, but at high values of input 2, we're getting a different delta on that modification. So that modification is more powerful in certain cases than others. Now, I don't know what input 2 is, but say it was a ride height, it's saying that potentially if you had a low front ride height, it is more dominant than if you have a high ride height. So it gives a more careful tuning of how the modifications could be used to achieve what you want to achieve. Okay, so the last sort of little bit is really going back to the validation. So what I showed before was, how does it predict the data we already had? But in reality, we want to say, well, how well can it predict data that we've never seen? So we sort of have to unsee some of this data. So this is a technique called K-folds, which is standard of machine learning. And this is just for one car rather than the full co-regionalized model. And what we do is we take all the data and put it in a random order. So the data points are just shuffled up randomly, and we divide into 10 buckets. And we're going to call these folds. And so what we do is we take the first bucket out of the data, and we regenerate the model using the other 9 buckets. So we have a model that's based upon 9 of the 10 buckets, and then we test it against that first bucket we've taken out. And that's what we're doing here. So every single one of these points is a prediction of compared to actual for a bunch of data that the model has never seen. So you can see the RMS error has not really changed that much. It's gone up a bit, but it's doing a pretty good job of predicted data that it never saw. And on the right here, what we've got is how those varies over the folds. That turned out, this fold 5 and 6, we just got unlucky. The data we took out was probably quite critical to the model. So without that data, it's harder to predict it. But we still only get a 1% RMS error, and most of the time we're down in the 0.5%. So the one thing we haven't done, which is the real test, is to take the co-regionalized model and then McLaren to actually do CFD on a new vehicle, say perhaps do 10% of the normal CFD. Put that 10% of the CFD back into the co-regionalized model and predict the other 90% that they were going to do, and then go and do those 90% of the CFD runs and check whether they match. So that's the one thing that we really would like to do at some point in the future. We're reasonably confident it will work well, and if it does, then clearly you can save a lot of CFD. Just a very quick thing, so I appreciate we're running a little bit over time about the implementation, because it sounds perhaps a little abstract. As I said, a lot of this stuff is openly available. We use the GPy Gaussian process regression code from Sheffield. And some of those people ended up working for Amazon Web Services. So Amazon make this available, a wrapper around GPy and other stuff, a nice piece of software called EmuKit. So if you get time, have a look at the EmuKit website. It does a really good explanation of some of these techniques. The other thing is we run it all in a thing called a Jupyter Lab notebook. So this is running within a web browser, and it's a very easy for the engineer to modify, adapt, interact, plot graphs, etc. So just to show a quick screenshot of that, this is what it looks like when it's running. So what you need to remember is what you're seeing on the screen here is not an application running on a PC. This is all running within a web browser. So the complete thing is in a web browser, and hence can be hosted elsewhere. It doesn't have to be hosted on site if you don't want to. And this is bits of Python in the blocks that say 1, 3, etc. But it's a notebook, so the bits here are markdown, so we can put documentation, equations, hyperlinks, etc. And all the plots get embedded in the notebook. So when you run the notebook, it's a complete documentation of what you're doing. So essentially what Joe did was created a bunch of tutorials for each of the functionality. And you can see here's the line plotter. So if the engineer goes in and changes that car A to car B and hits return, these graphs below will regenerate. So it's very easy for the engineer to take those tutorials and modify them to what they want. And the functions that we're actually calling underneath are sort of more hidden, so we wouldn't expect them to be modified. But the front end is all interactive and so running through just a web browser. And the other thing that we did was a little thing that if you added new data, you just had to create a file with it called, the name of the car, so car.xlsx, pop it into a folder, and then the code would spot there's a new file appeared there, read it in, regenerate the model, save all the parameters, and then carry on. So it's very easy just to add data to the model, which is what you want to do. You want to keep adding data as you get new data. Okay, so sum up, what have we achieved? We've successfully generated, validated, bespoke and co-regionalized models. And essentially what we can do is create a complete error map, including uncertainty from a few new CFD points and as much past data as we can get our hands on. We can do classic delta type things, predicting wind tunnel from CFD, but not just as a constant, as a delta that itself is a function of the car and a function of the geometry, and also assess impacts of discrete modifications. And we can rigorously tell people how important certain parameters are in determining the outputs that you might be interested in based upon the data rather than a preconceived conception. As I said, the large amount of data is key. We're a bit marginal in terms of the number. 7 input parameters and 800 data points is a little bit marginal on what the recommendations would be. So it is important to use whatever you can to get more and more data into these to make the models better. The other message is, you can see I have anonymized things, but that was how we started. Actually, we didn't know what any of these parameters were, and it doesn't actually matter. It's just a column of data. And in fact, internally, machine learning tends to normalize everything as well. So internally, it's normalized data as well. So it's anonymized, normalized. So you can perhaps see how easy it could be to adapt this, not just to any other aerodynamics, but any other engineering application. Okay, so I'm going to stop there. Thanks everyone for listening. And in a little while, we'll be able to answer some questions for the Q&A.
Lovely. Gary, thank you ever so much. You covered a lot of the ground in your presentation.
Yeah, so apologies a bit long, but
no, not at all. No, it was fascinating. Actually, it's really good to see the project making some great steps. Actually, I think you know, we're always talking about digital engineering being about doing things better, faster, cheaper, and this is one of the projects that you're really being able to demonstrate the power of potential AI or machine learning in this case to do that. And you know, we always talk about one of the biggest opportunities around machine learning is the ability to move much more of what we do in the physical world into a digital world, and therefore test more of the use cases, reduce the cost of prototypes, and obviously improve the time that it takes to bring new product to market. And this is a great project that literally does touch on all those 3 areas of better, faster, and cheaper. So it's great to see. We're now joined, well, we welcome back Piera, obviously, to the screen. We're also joined by Eve from Loughborough University and Arthur from McLaren. So welcome to both of you. Thanks for joining us. And we have got a few questions coming in, so we'll get stuck straight into those. Now, with our webinars, for those of you who are familiar, we try and be a little bit brave. So rather than me boringly ask questions from the audience, we try and bring them live. And our first question is from Kenny Maddox. So if we can try and bring Kenny live, then he can ask the question himself. Kenny, who are you pitching your question at, and what's your question?
Morning, everybody. My question's for Gary. It's actually so I think, Gary, is the plan to link the parameterization of the geometry to kind of a generative design package to kind of guide aerodynamic design of the shapes, and then also start to input targets for a vehicle to that? And then also a quick follow on to that, what format does the data need to be in? And have you had any issues with errors thrown off results, and how did you manage that?
Okay, so I think I'll answer them backwards. So the data itself is pretty simple. It's just a spreadsheet. It literally is a spreadsheet with columns of data. And we've actually tried it on some completely different data. It's nothing to do with engineering on it, just to see how it works. And yes, we have had some little things. So occasionally the model was behaving badly and we couldn't quite figure out. And then when we looked, we did find some errors in the data that Piera, I hope she won't be ashamed, found there was a slight error in a couple of data points, and fixed them, and the model started working okay. So if you do get the model not behaving correctly, it's possibly because the data is a bit flaky. In terms of the first one, yeah, if we can follow up this work on, I think that's exactly what you could do. There was a slide I took out because it was getting quite long. The MU kit has got a thing called Bayesian optimization you can do. So if you did, say, you got a new vehicle, you did say 3 or 4 CFD tests, it can then predict the, look at the design space and predict an optimum with uncertainty, and then it can then tell you where to do the next CFD calculation of the design space to narrow that uncertainty. So it can tell you where an optimum would be, but also where you need to run your next calculations to improve the confidence in the optimum. So it's actually in there. We just haven't even touched upon that functionality.
Excellent. Thanks, Gary. Good. Does that answer your question?
Yeah, that was great. Thank you very much.
Thank you very much indeed for your question. Next question is from Richard Amunagama. Richard, we're going to try and bring you live as well, I believe, if we can. There he is. Richard, who would you like to ask a question to, and what's the question?
Hello, this is Richard Amunagama from Apollo Future Mobility. The question is to Gary, as he's the only one who's spoken in depth so far, so apologies to the other guy. The question is actually how does your process deal with contradictory data? So data that's correct, but on a certain vehicle it produces one result, so an increase in drag, for instance, and on another vehicle it produces the opposite result.
I think that's what I was touching on previously, that if you have data that is like that, the model can behave quite badly. And so that's a key thing with these things is making sure if you do regenerate the model to do through validation to check it's still behaving correctly. It depends how contradictory they are, in the sense of if it views it as noise, then it will essentially fit through that rather than trying to, sorry, it will essentially take the average rather than trying to fit to that. And that's why some of these length scales and other parameters are quite important. The other way you could get contradictory results is if you essentially get, say those 6 input parameters, we had 2 data points for 2 different answers. It's essentially saying there's an unknown parameter that we don't know what it is that made it change. The 7th parameter must have been the thing that caused the lift to be positive in one case and negative in another. And so you do need that parameter. So it's just suggesting that there's something unknown in the data that creates that contradictory result. So yeah, so it depends upon how contradictory, but and it is important to understand that.
Does that answer your question, Richard? Are you happy with that?
It does. Would it be all right to have a follow-up to the McLaren team based on that? I'm assuming the team at McLaren's starting to use this in anger. So I'm just wondering how you avoid falling into the trap when you're busy, which is always the case when you're in a development program, of not just accepting the result, but trying to work out why you're seeing what you're seeing. Because there's always a temptation when you start to adopt these tools of just accepting it, making a change, moving on, and if it's in kind of the right direction, you're happy.
Who's best to answer that one? Is that one for Piera or?
So the question is, how do we avoid falling into the trap of just using this in anger without double checking our results?
Yes, when you're under pressure and you start to build confidence in this, kind of how do you avoid that trap of just accepting it? Because I've worked in a lot of teams where they take the CFD result, that's true, move on. Obviously they'll do a run, but they don't understand, they don't take time to understand what's come out of it.
Yeah, I mean, I think it's a very good question. Thanks for asking it. I think that, it's we kind of have to take a step back from just treating this as a black box, and you have to think that you have quite a lot of experienced engineers working on each vehicle and each project in our thermal team. So normally, as engineers, we try really hard to understand what's going on. So we don't take numbers as they are. So yeah, pressure is always a risk in adopting whatever the computer is telling you as the absolute truth. But we also have very, very experienced engineers that help us, that effectively try to avoid falling into this trap. And I think in my experience, really also working in aerospace, it doesn't happen very often, really, to actually just take a result for granted. And that's probably what makes the difference between a good and a bad engineer. I would go as far as that, like not just take the numbers for granted, but back it up with the first principles understanding. So it is a risk for sure, but that's kind of what makes, in my opinion, the difference between being a good engineer and a bad engineer. And yeah, so that's kind of my answer. I don't know if Arthur wants to expand on that.
Yeah, no, I agree completely. It's you've got to combine the two things. And I think for me, the uncertainty bands are also a key element to that as well. To really understand the quality of the data that it's matching to. As Gary described in his section, where you have data points lacking, we get a better understanding on the quality, the uncertainty of that on map.
Okay, Richard, is that useful?
Yeah, it's a great answer. I think it underlines the importance of keeping humans in the loop, and you can't rely on AI and simulation as much as they're a buzzword to carry on automatically.
I know, I totally agree. I think the term artificial intelligence I always have an issue with. I prefer the term augmented intelligence because it suggests ultimately there still has to be a human in the loop to make the final decisions. And I think machine learning is fantastic and can certainly accelerate or drive much greater insight faster. But ultimately, you still need a human to interpret it and make the decision off the basis of that augmented intelligence. Okay,
Thanks a lot.
Thank you. Next question is actually, they can't come live, and I'm not even sure who the question is to, so I'll throw it open. I suspect it might be for Gary again. It's from Sam DeGuido. Is this approach specifically applicable to automotive, or can it be used in another sector, e.g. aerospace and other engineering areas, so structural rather than aerothermal?
Yeah, I mean, I was trying to emphasize that at the end. In some respects, the software is completely blind to the source of the data. So in principle, it can be used for any type of data where you've got inputs and outputs. Clearly, as someone who pointed out, it's a bit dangerous just to blindly use this stuff and create a model and use it. And you need a lot of go through the same sort of processes of checking the model's behaving and it's doing what you expect, and you're not getting any odd behavior. But in essence, it's data fitting, and it doesn't really care about the underlying physics. You know, clearly things that behave rather smoothly and whatever is better. You know, things that have certain jumps and the like would struggle to a certain extent. But that, I think there are tools, you know, further developments of these methods that would deal with that as well. So no, I think there's no real reason you couldn't use it for any other type of engineering if you have the data, if you have plenty of data.
Brilliant. Okay, thank you. The next one is actually to Eve. We've got a question for you here, if you can. These methods have been, and it's an anonymous attendee, so we don't have the name of the person asking for this one, but these methods have been used extensively by F1 teams and aerospace companies over the last 10 to 15 years. What would you say was new about this work? Slightly controversial question.
Yeah, I think we only had limited time. That's why Gary was showing the research associates were only using standard toolboxes. There were a lot of scopes that we can extend to involve the new research element in. Like Gary identified, we can introduce methods to identify the new kernels, or to find the optimal kernels or the optimal hyperparameters. Those ones would be new. So we started the discussion with Gary, with the research associate Joe as well. And that would be a little bit of the future work. Because of the limited time, actually, we were just trying to do something practical with the existing machine learning toolboxes, and then fine-tune the hyperparameters according to this application.
Okay, no, thank you. No, and yeah, it's a slightly controversial question, but I think, you know, generally we see these things do cascade down from Formula One teams, and obviously, although Pierre and Arthur can't talk about that today, obviously they also have a Formula One team that I'm sure they're hoping perform extremely well this season. That's just about to start. But certainly, you know, my background is Aston Martin. Again, we do see a cascade of technology from, in Aston Martin's case, Red Bull, through to the business. So that is sort of normal. But generally, there are slightly different priorities in Formula One to the normal automotive divisions, but that cascade is quite normal. Interesting enough, there's some other questions, but I'm going to be selfish and as moderator ask a question myself, which is a sort of a cultural one, to maybe Arthur and Piera. What level of sort of cultural pushback have you had on some of these new methods within your aerodynamics department, or you know, because obviously what we're suggesting is that we do less physical prototype testing and move more of that work into a computer. Has there been any pushback on that, or any skepticism within the function in terms of accepting some of these new methods?
Like if they went to Piera.
I mean, I really like McLaren for the courage to take brave decisions. So I wouldn't say that there was an extreme pushback. And, you know, McLaren is a relatively, automotive is a relatively new company. And so taking kind of a leap of faith into these new technologies is, I think, what makes the brand really exciting. So I wouldn't say that there was a huge pushback. And in fact, we're one of the, and I think it is with every project, really, we have to make kind of research, not just for the sake of it, but really to find an applicability. And I think that once we demonstrated what this could bring in terms of saving time, saving costs, and help us actually accelerating the way we design our products from an aerothermal point of view, there wasn't really no pushback. So yeah, no, in essence, I don't think that there was a huge amount of pushback. Yeah.
Go on,
Yeah, I would add one of the key benefits of this is that it helps with automation as well. So because it is just data, so there's real big opportunities to automate a lot of these processes. When you're just getting data straight off the car and getting it processed with minimal, you know, manual input.
So essentially achieving insight faster by letting computers do the heavy lifting on the data analysis and the data science?
Yeah, which any engineer would only enjoy.
No, I totally agree. No, that's interesting. And again, on the cultural side, you know, I would hope that McLaren, I would expect to be much more open to some of these new technologies. And you know, I think certainly we're seeing that cultural barrier being there in some of the less technologically advanced companies, I think, in terms of accepting these new methods. So it's good to hear. But again, I'd be surprised if you were getting a lot of pushback, certainly given the sort of company that you are. But no, thank you. Question again again, this feels another one either for Gary or for Eve, and it's from David Massiger, who I don't think we can bring live. We can't get his confirmation that we can bring him live, and obviously we don't just fire people into the live environment without their permission. But the question is, and Gary, you can decide whether you want to delegate this onto Eve or not. Why did you choose Gaussian process rather than against other machine learning methods?
I'll start.
Yeah, I think I was just answering that in the chat box. I didn't.
Well, you got the opportunity to.
So we chose Gaussian process regression first because there were only limited data available. There are a lot of advanced machine learning models like deep learning, convolutional neural network, recurrent neural networks, etc. That those advanced machine learning models that you heard, they are only suitable for a large amount of data. We are talking about millions or tens of millions of data points. So when we were talking with McLaren, it started with 100 data points. So we started with this Gaussian process regression because it's suitable, it's flexible to do the regression for a small amount of data. And the second part is it has an advantage. It gave a prediction interval. So it tells you like the uncertainty of the model fitting. And the third advantage is when you bring in more data points, 2 more points, and they become more accurate, and more data points, they become more accurate. So it's mainly because the flexibility and the uncertainty, it gives you the uncertainty, which provides insights for machine learning scientists, also for the engineers in the company as well.
Fantastic, thank you, Gary. You
well, yeah, just to follow on to that. I mean, I think perhaps what perhaps hasn't come across is this was a relatively short project. The whole Gaussian process regression was about 3.5 person months of time work in it. So, and in fact, the Gaussian process regression, Eve tried early on in the project. It was looking quite good. I did try running some data through an artificial neural network, and it was just terrible. It just wasn't enough data for it. So if we had more time, clearly we would try more techniques and prove that this is the best one. But it was certainly the one that Eve picked up straight away, worked pretty well, and we just ran with it and got something out of the door.
Brilliant. Thanks, Chris. Sorry, Gary. I was looking at my from Chris. Again, we're going to go brave and try and bring Chris online. Chris, I think we know each other, don't we, Chris? So you should be live. Welcome. And who would you like to answer your question to? You there, Chris? I can see that he should be there. Chris, if you're muted, you might be muted.
Hear me now, Bradley?
Oh yes, Chris. Yeah, you're there. Hi, Chris.
So there's something wrong with my microphone. Anyway, yes, morning, and hello, Richard, and other people. Arthur, hello, I've met before as well. So error can be hugely non-linear, with big changes in aerodynamic outputs for small geometrical changes. You know, for instance, if you put a strake onto a diffuser or a splitter or something like that, by its very nature, it's a non-linear element, non-smooth. It looks at the moment that the application, Gary, that you've put together is used for error mapping, reducing the CFD requirement to populate the operational envelope. Does I guess, from Gary's point of view, do you think it can be applicable into a design space where you may encounter these non-linearities? And I guess to McLaren, do you have the ambition to expand the technique into this kind of area?
Yeah, so I think you're absolutely correct. I think, you know, that non-linearity in aerodynamics is probably what's kept a lot of us in jobs for quite a long time. And if, you know, and so it's, if we had more time and more data, that was something we look at. In actual fact, before we'd had the real McLaren data, we did generate a synthetic data set based upon aerofoils and aerofoil stalling. And so we were predicting stall behavior based upon thickness and camber correctly from the model. So that's non-linear, but not as dramatic as perhaps as some of the other examples. So I think it clearly needs a lot of exploration. And I guess it's the health warning, isn't it? In terms of if the model predicts something, if something non-linear is going on that the model has never seen, it really can't guide you in the right direction. So I guess there's a health warning on the answer.
Chris, does that help at all?
Yeah, I mean, I think that backs up my thought. I mean, I guess in the aerothermal space, also one of the most complex things may be the transition from laminar to turbulent, and therefore looking at the heat transfer impact of that and whether the models can pick those kind of things up. So I mean, I'd 100% agree with what Gary says. It's a complex thing, but yeah, it's really interesting to see what's going on and the collaboration between these two companies, or the university and McLaren. Thank
you, Chris. Thanks for joining us today. Thanks for your question. Okay, I've got an anonymous question, but again, it takes us in a slightly different direction, so I like these ones, which is more around academic, actually. So I'll throw it open, though, because I think that many people will have some views on this. To work on this kind of projects, is it necessary to be studying a more computer science-related degree, or could a mechanical engineering student work on these types of methods? So again, this is one of the big discussions around digital engineering, is how do you get into it? Because it is a blend of many different things, and the world of engineering is changing, and therefore maybe the skill set that you're going to need in the future to be an engineer or a new breed of engineer are slightly different. So Gary, I guess you can answer sort of academically, but it would also be interesting to get maybe Pierre and Arthur's view on where they're finding skills to do this sort of work as an employer as well. But Gary, do you want to sort of start as a professor amongst us?
Yeah, so I mean, it's a very good point, and indeed, you know, that's something we recognise in terms of teaching. And so Eve is just launched a new module. She's been running for the first time on machine intelligence, which is aero and auto engineers being taught this sort of stuff. In fact, doing. So I think Eve was using the example data set we had for the aerofoils as part of a piece of coursework. So we're actually starting to teach this sort of stuff just to third year students. In terms of actually doing what we did, Joe is by background a mathematician, not an engineer. So it is multidisciplinary. So in terms of the team, I brought, probably least to the table in terms of the aerodynamics. Eve brought a lot to the table in terms of machine learning, and Joe brought a lot to the table and actually be able to do some quite hard maths. There's a lot of hard maths in this that I struggle with. And so I think at that level, you do need a multidisciplinary team. But ultimately, I think in terms of doing some things, I think, your engineers, that's what we should be producing as engineers of the future that are very comfortable with this type of stuff, rather than knowing about panel methods, which is not really much help to anyone.
Understood. Again, Pierre, Arthur, from an employer point of view, where are you tending to draw people that are good at this from? Is it from a mechanical background, or are they data scientists or IT? Your insight is useful.
Yeah, I would probably echo Gary's points. So they are two different disciplines, but they do need to be moving together. So the mechanical degrees need to definitely be doing more in the data science area going forwards, rather than panel methods, as we say.
Do you think that going forward that again, are you tending to pull people from other sectors as well, or are you seeing more and more pollination cross sectors in some of these new methods and processes?
Yeah, I think it really is quite dependent on the individual, I would say. I'd be curious when Pierre's thinking kind of engineering background.
Yeah, I mean, I come from an aerospace background, so I didn't know much about automotive when I joined McLaren. But I think that kind of the definition of engineer as kind of a strict term is kind of changing really, and rather than calling ourselves engineer, I think we should call ourselves scientists, because effectively what we do are experiments, whether they are physical or numerical. Then try to prove our hypothesis, really. So the boundaries are kind of becoming more and more blurred, and machine learning and in general artificial intelligence, in my opinion, is becoming really something like in everyday speech. Maybe 5 years ago it wasn't like this, and it was more of a niche. And now actually, I mean, we're talking about making advanced statistics effectively. So I still think, that it's good to have a solid foundation of maths, physics, and statistics, which are effectively the language that we speak. And then how that's applied, I think, it can be applied anywhere. So it's really about a mindset more than a label on your degree. So, I mean, I wouldn't say this work can only be done by computer scientists or only by people that are very, very close to machine learning. I think, that as long as you've got a good maths, physics, and statistics background, then I think it's very accessible.
No, okay, that's really useful actually to hear. I think that without a doubt, I think the critical path to any program development, though, I think is becoming clear that it's less around the mechanical assurance, and it's going to be more around the assurance of software, as the likes of cars and all of our products is growing exponentially. And even with electrification, one could argue, and I know you can't comment on this from a plan point of view, but generally cars, and I'm a powertrain engineer, so but cars are becoming simpler. Don't tell the people working on battery electrification, but the mechanical challenges are simpler. They haven't got to wrestle with cooling, fueling intake, and exhaust and emissions in quite the same way. There are some different challenges, admittedly, but the mechanical aspects of product development are becoming simpler. The challenges are moving into the world of software and developing products that are capable of learning on the fly, and how we update those products while they're still in the customer's hands. Those are becoming some of the bigger elements that we have to wrestle with as engineers and developers of product. And I think that's where some of the more traditional skills that are taught in mechanical engineering courses, I guess, have to broaden, as you say, to suggest to focus more on how we use data, not just as part of the engineering program, but how we use data across the life cycle and across our enterprise. Yeah, I agree. Yeah. Okay, that's it. I think we're going to draw the questions to a close then. Do you what are there any final comments you guys want to make about the project, or shall I just close off? Gary, anything you want to add? or have you covered everything you want to?
I think I've spoke plenty.
Excellent. Garrett, anything you want to add to that? Anything?
No, I mean, I just wanted to say that this project has been very short, but it's been really useful and kind of a very different from what I do from my day-to-day job. But yeah, no, I just wanted to thank Gary, Victor, Joe, and ID, of course, with James, Mary, Sam, and yourself, Bradley, for the opportunity. It was a brilliant 9 months. Yeah.
It's very kind. Thanks, Pierre. Arthur, any final comments from yourself?
Yeah, no, I think the project's really benefited from the different disciplines and people that have been brought into the project. So,
excellent.
Quite often it's been one discipline or the other. The multidiscipline approach has worked well.
Excellent. Thanks, Arthur. And last but definitely not least, Eve, anything further you'd like to add?
I'm just glad to be involved in this project. It's always nice to see machine learning models can be applicable in real industry applications. It's just nice to see some good results. Like said, there are a lot of research elements that we can further develop, but maybe in a later stage. And thank you, IDE, for support this project, of course.
No, it's, I mean, it has been an interesting one. Obviously, it's always great working with a brand like McLaren anyway, but I think even the subject area has been fantastic. And it is just the start, I think. I think we're still just touching the surface on some of this capability. So obviously, we'll be exploring what we do next with McLaren when this project does come to an end. I think the other interesting bit is we've just kicked off another project actually on machine learning with Ford on the next generation Ford Transit. It's in a different area, so it's not aerodynamics, it's around how do we predict failures in large fleets of vehicle? So it is on the other end of the life cycle. But we've introduced a small company who again found great traction in fintech and pharma, but we're struggling to get a foothold in the automotive industry. And we're seeing some fantastic early signs of what this company is starting to deliver. And we've really got the attention with Ford globally about some of the exciting capability or that could be unlocked using machine learning by using it to create insight from field derived data. But again, we'll come and hopefully do another one of these events over the next few weeks. But I'd like to thank all the presenters, fantastic, and obviously Eve and Arthur for joining us.